Hello everybody, welcome back to Monte Carlo Methods. In today's video, we are going to learn how to simulate from any one-dimensional discrete distribution, whether it's the Bernoulli distribution, the binomial distribution, the geometric distribution, the Poisson distribution, the negative binomial distribution, the hypergeometric distribution, or any discrete distribution that you want to make up and put your name on. So let's get right into it. I'm going to suppose that U has the continuous uniform 0, 1 distribution, and I'm going to lay out an interval here from 0 to 1. Now you know this uniform random variable is equally likely to be anywhere. So if we consider the first half of this interval from 0 to 0.5, and I ask, what is the probability that U falls in the first half of the interval? The answer is, of course, is 0.5. And if I switch this up a little bit and maybe look at an interval from 0.2 to 0.3 and ask, what is the probability that U lands between 0.2 and 0.3? The length of that interval is 0.1. This is in fact 1/10 of the entire interval. And because we're equally likely to land anywhere, the probability that the uniform lands in the interval between 0.2 and 0.3 is 1/10 or 0.1. Let me just make this a tiny bit more complicated. Suppose that I am looking at a set of values that consists of two disjoint intervals, say between 0.5 and 0.55 and 0.97 and 1. And now if I ask you, what is the probability that U lands in this set? The answer is, of course, the total length of these intervals here divided by 1, which is the total length of the overall interval. So we're looking at 0.05 plus 0.03. The total length of the set defined by these two intervals is 0.08. And so the probability the uniform lands in this interval is 0.08. Now, if I was trying to simulate an event happening, maybe a success or failure event, and the probability of success was supposed to be 0.08, one way I could simulate that event happening is to grab a uniform and to lay out this very strange looking set of intervals here. This would actually be a weird way to do this. And anytime the uniform falls in this set of two disjoint intervals, I would output success. So that's the idea behind all discrete one-dimensional random variable simulation. Let's look at an example. Suppose that X is a random variable taking on the values 1, 2, and 3 with the probabilities 0.2, 0.5, and 0.3 respectively. How are we going to simulate values from this distribution? Just as a reminder, what is it going to look like? The output of our algorithm should have 1s and 2s and 3s. It should have 1s 20% of the time, 2s half of the time, and 3s 30% of the time. So one way we can do this is to look at a value drawn from our random number generator, which is a realization of the uniform 0, 1 random variable, and chop up the interval between 0 and 1 into 3 different intervals that have lengths 0.2, 0.5, and 0.3. Whether or not you want to do them in order or in a contiguous way is up to you, but the most natural way to do this would be to look at the interval from 0 to 0.2, and then 0.2 to 0.7 for a total length of 0.5, and then 0.7 to 1 for a total length of 0.3. So now you know what to do. You're going to use your random number generator to simulate a value U from the uniform 0, 1 distribution, and if U falls in this first interval from 0 to 0.2, you're going to output the value 1. Whereas if U falls in this second interval of length 0.5, you're going to output the value of 2. And finally, if your realization from your random number generator falls in this interval from 0.7 to 1, you're going to output the value 3. This way, you're going to get an output of 1 20% of the time, 2 50% of the time, and 3 30% of the time, and get a new uniform, repeat the process, get a new uniform, repeat the process. You're going to get a list of 1s and 2s and 3s in the right proportions, and that's how we can simulate values from this distribution given by this table over here. I call this idea interval chopping, so you may hear me refer to interval chopping again in the future. And I claim that we can do the same thing even if the distribution has infinite support. As an example, I'd like to look at the geometric distribution, or at least one of them. There's two common geometric distributions, one that starts from 1 and one that starts from 0. For this example, I'm going to look at the one that starts from 1. This has an interpretation as if you were to do several independent trials of an experiment where the outcome at each trial is either success or failure, and the probability of getting success on any one trials is p. If you want to count the number of trials until the first success, that would have a geometric distribution with this probability mass function. And it's really easy to figure this out because you'd say, what is the probability that I only take one trial until my first success? That's the probability you get success on your first trial. That's probability p. So the probability that x equals 1 is p. And that's what you see in this formula. Whereas if you want to say, what is the probability that the number of trials until my first success is 2, that would mean you'd have to get a failure and then a success. And with the trials being independent, that would happen with probability 1 minus p times p, which is what you see here in this formula when you plug in x equals 2. So this is a geometric distribution, the other geometric distribution being the number of failures before the first success. And it's possible to get success on the first trial and have 0 failures. So that distribution would also have x equals 0 in its support and a slightly different exponent. But we're working with this one, and there are an infinite number of possible values. I want to do this with the interval chopping technique. Here, this lowercase p is a parameter. It's some fixed number between 0 and 1 that is known to us. So how are we going to do this? I just said we're going to use interval chopping, but you don't want to try to take your interval and chop up all the probabilities all at once because there's an infinite number of them. So what you do is just look at one interval at a time. The first interval here would correspond to the probability that x equals 1, which is a lowercase p. So I'm going to grab a value u from my random number generator. I'm going to recall that the probability that x equals 1 is p. So I'm going to put p down on my interval here. And I'm going to say if my uniform falls in this interval, then I want to output the value 1. If not, I am going to create the next endpoint for the next interval. So note that the probability that x equals 2 is p times 1 minus p. So I'm going to make another sort of segment here. I'm going to go from p up to whatever value I need to go up to get a total interval length of p times 1 minus p. So we need to go up to p plus p times 1 minus p. This is an interval of length p times 1 minus p. And if your uniform falls in this interval, then that's going to happen with probability p times 1 minus p, which is going to correspond to the probability that x equals 2. And so when you see your uniform fall in this interval, you want your algorithm to output the value 2. And you just continue in this way. By the way, if you want to know whether or not your value u fell between p or p plus p times 1 minus p, presumably it did not fall between 0 and p if you are incrementing the little parts of your interval in this way. So once you have ruled out that you cannot output x equals 1, then your uniform was definitely not between 0 and p. So when checking that it's between p and p plus p times 1 minus p, you really just need to check that it's less than or equal to p plus p times 1 minus p, because you already know it's not down here. So by checking that it's less than or equal to p plus p times 1 minus p, you do know that it's in this interval. So you continue in this way until you get a hit, until your uniform actually falls in an interval and you get an output value. And then you grab an entirely new uniform from your random number generator and start the process all over again to get a second draw from the geometric distribution. Now, for the geometric distribution, like most distributions, we do have other options. So one alternative approach would be to use the interpretation of the geometric distribution. Remember, I said that you have a sequence of independent trials of an experiment. You have 2 possible outcomes on each trial. We usually call them success and failure. You have some probability, little p, a fixed parameter between 0 and 1, inclusive, which represents the probability of getting success on any one trial. and x is the number of trials until the first success. So all you need to do is, and I say all you need to do like this is a good idea, I actually don't think that this is any better than the interval chopping approach. It's just an alternate approach. But all you need to do is grab a uniform 0, 1 random variable. I'm going to call this u from your random number generator, and then look at a success probability and a failure probability. In other words, chop up the unit interval into only 2 pieces. Now, if your uniform falls down here, you're going to call it a success. And if your uniform falls up here, you're going to call it a failure. And if you get a success on the first try, you can say that x was 1 because it took me 1 trial to get a first success. But if not, you throw out that uniform and you grab another one and you figure out, is it down here or up here? And you keep doing that until the first time you find a uniform down in this lower part of the interval, and you count how many tries it took you to do that. Now, this is going to require several uniforms, unlike the other approach that requires only 1 uniform to get 1 geometric draw. So there's no real savings by doing it this way, but it is an approach we can take by going back to the interpretation of the geometric random variable and its distribution. So I have one more approach, which is very specific to the geometric distribution, but it's super cool and slick and fast and does only require a single uniform. And this is for you to note that if capital U has a uniform 0, 1 distribution, so this is still a random variable here and not output from a random number generator that has been observed, then if you form a quantity out of this, which would be the natural log of u over the natural log of 1 minus p, and then put the ceiling function around this. So what the ceiling function does is take whatever value this produces and round up to the smallest integer above that number. So if you get 5.3, you want to round up to 6. I claim that this has this geometric distribution starting from 1 that we just talked about. So let's prove it. First, note that the quantity inside the ceiling function, the natural log of u over the natural log of 1 minus p, is greater than 0 because the natural log of numbers between 0 and 1 is negative. So this uniform is between 0 and 1, and 1 minus p is between 0 and 1. So you actually have a negative over a negative here, which is positive. So we know we're going to get positive values for this. And then when you take the ceiling function of that, your possibilities are going to be 1, 2, 3. There's no way to get a 0 because you're going to get something positive and you're never going to round down to 0. So you get the values that are in the right space for the geometric distribution that starts from 1. So that's the first thing to note here before actually proving that we're getting the right distribution. We're at least getting something with the same support as the support for the geometric distribution. So what is the probability that this quantity gives you any particular value, little x, where little x can take on the values 1, 2, 3 on up? So if the ceiling function of this quantity is equal to x, that means that this quantity is greater than x minus 1 and less than or equal to x. In other words, if this thing is going to pop out the number 6, then what you had to observe is something greater than 5 or less than or equal to 6, so that when you take the ceiling of that, you get 6. So this is my first step in sort of trying to isolate the uniform u, because I do know how a uniform 0, 1 behaves, and I can easily compute probabilities for it. I'm going to continue to try to isolate this. The next thing I'm going to do is take this denominator and multiply it all the way across. Now, because the little p is between 0 and 1, and let's assume that it's not actually equal to 1. If it is, then you really don't need to be doing this sort of simulation because you're going to get success on your first trial. So let's assume that this is some finite number and we're not dividing by 0, but it is negative. So when I multiply it all the way across, I will flip the inequalities and we will end up with something that looks like this. In the next line, I am going to reorder this. I'm just going to put this on the left and this on the right, so the inequalities are going in a nicer direction, but I'm also going to use the fact that, like, the log of x to the a is a times the log of x. In other words, these coefficients in front can go up and be powers on the 1 minus p. So we get that this is equal to the probability that the natural log of 1 minus p to the x is less than or equal to the natural log of u is strictly less than, and the strict inequality is not really important here because everything's continuous, but is strictly less than the natural log of 1 minus p raised to the x minus 1. Continuing with my goal to sort of isolate that u, I'm gonna take e to every part of this. E to the x is a monotone function, so if you have like x less than y, then e to the x is less than e to the y, and so I will not disturb the inequalities when I take e raised to all parts of this. And now I have an e and a log, and I'll get cancellation. So I've got the probability that 1 minus p to the x is less than or equal to capital U is less than 1 minus p to the x minus 1. And I know that these numbers are between 0 and 1. And I also know that they are in order because 1 minus p is between 0 and 1. So the higher power you take of it, the smaller the number is going to get. So this number is smaller than this number. And how do you find the probability that a uniform is between, 0.4 and 0.7? It's just the length of that interval from 0.4 to 0.7, which is 0.3. So in this case, I get the length of this interval. I get 1 minus p raised to the x minus 1 minus 1 minus p to the x. So in summary, what we've done so far is we said that the probability that the quantity, the natural log of u over the natural log of 1 minus p with the ceiling function around it is equal to an integer x, where x could be 1, 2, 3 on up. We just worked out that this is 1 minus p to the x minus 1 minus 1 minus p to the x. I am going to factor out a 1 minus p to the x minus 1 from this expression, and this is going to leave me with a 1 minus a 1 minus p, and 1 minus p is, of course, p, so we get p times 1 minus p to the x minus 1, which is exactly what we wanted. This is the probability that a geometric random variable starting from 1 with parameter p is equal to little x. In other words, we have just proven that this random variable quantity over here has the geometric distribution starting from 1 with parameter p. That's exactly what we wanted. And so if you want to simulate values from the geometric starting from 1, you could grab a single uniform from your random number generator and compute this quantity, output it, and you're done. This is 1 or 2 lines of code, super easy, super slick, but I'm not sure how useful it is for you to know this. I just thought it was fun because this is just so specific to the geometric distribution. It's cool though, and give it a shot. Let me know what you think. Note that for the geometric distribution that starts from 0, you can in fact just take the output here and subtract 1, or you could take the log of u over the log of 1 minus p and look at the floor function, which is going to round down. Now, I don't know how obvious this is to you, but we can certainly prove it in the same way we just proved that this probability of getting little x is equal to p times 1 minus p to the x minus 1. If you did the same sort of thing with either of these two expressions, you would end up with p times 1 minus p to the x, where x could take on the value 0, 1, 2 on up. And so you could simulate from the geometric starting from 0. So let's talk about a few other common distributions. The Bernoulli distribution, this one's going to be super fast. If x has a Bernoulli distribution with parameter p, this means that the probability that x equals 1 is p. The probability that x equals 0 is 1 minus p, and you don't get any other values. So you can just use simple interval chopping and break up the interval from 0 to 1 into an interval of length p and an interval of length 1 minus p. Grab a single uniform. If it's down here, output the value 1, and if it's up here, output the value 0. Super easy. Nothing new there. Let's talk about the binomial distribution. If x has a binomial distribution with parameters n and p, that means the probability mass function looks like this. So some things you can do, you can use interval chopping. It's not bad at all. There are only a finite number of values, but I would still probably approach this as we did in the infinite number of values example. So I'm not going to chop up the complete interval into n intervals. I'm just going to sort of check as I go. Another thing you can do is use the interpretation of the binomial distribution as the number of successes in n independent trials of an experiment where you get success or failure, and success happens with probability p. So we could, simulate each of those n trials and count the number of successes. That's not really going to save you much in terms of iteration versus interval chopping. And just for fun, and this I think is not really a useful thing, but there's so many cool relationships between distributions, especially with the binomial distribution and others. For example, if I let capital G1, capital G2, etc. be IID from the geometric distribution with parameter P, the one starting from 1. So I have a geom sub 1 here of P, and you usually see geom of P or geometric of P. You'll never see a subscript like this. This is my personal notation to distinguish whether or not I'm starting from 1 or starting from 0. But if you let x be the smallest non-negative integer such that the sum as I goes from 1 to capital X plus 1 of the g sub I is greater than n, then I claim that x has a binomial distribution. I don't think this saves you anything in simulation. I just thought it was kind of cool, so I thought I'd mention it. And I don't want to prove the whole thing. It's a little bit tedious, but I just want to look at a couple of values here. And there are many other relationships between other distributions, including some continuous distributions and the binomial distribution that you might want to exploit. But then again, I don't really think it's worth it if you can just do straight up interval chopping. So let's just prove a little of this just for fun. I'll get you going on this. What I'm going to do is look at the definition of capital X and just look at like the probability that capital X equals 0 and maybe equals 1 and see that we get things or probabilities that match the binomial distribution. To this end, note that if G1 has a geometric distribution starting from 1 with parameter P, then the probability that G1 is less than or equal to some n, this is going to be the sum as little x goes from 1 to n of P times 1 minus P to the x minus 1. So if I pull little p out, I'm left with a finite geometric sum. Go check out or recall your finite geometric sum formula. But in the end, you should get 1 minus p quantity to the nth power. So this is going to be helpful, I think, because the probability that capital X equals 0, remember, x is supposed to be the smallest value such that the sum as I goes from 1 to capital X plus 1 of the g sub I is greater than n. So if capital X equals 0, that is equivalent to saying that g sub 1 was greater than n right off the bat. But g sub 1 being greater than n, that probability is 1 minus the probability that g sub 1 is less than or equal to n. And from this up here, we know that this is 1 minus p to the n, and this is in fact n choose 0 times p to the 0 times 1 minus p to the n minus 0, which is the binomial distribution expression for the probability that x is 0. So this checks out. I'm going to look at just one more. Let's look at the probability that capital X equals 1. So capital X was supposed to be the smallest integer such that the sum as I goes from 1 to capital X plus 1 of the gi is greater than n. Now, if capital X is 1, that's saying that the g sub 1 was not greater than n. It was less than or equal to n, but g1 plus g2 is greater than n. So one way to deal with this probability here, these are not independent random variables. I have g1 over here and g1 over here. But one way to deal with this would be to condition on the value of capital G1. This is equal to the sum as little x goes from 1 to infinity of the same probability given capital G1 equals x times the probability that capital G1 equals x. So I'm going to plug in capital G1 equals little x here, and I'm also going to fill in our known probability mass function for the geometric distribution starting from 1. And we end up with this. I claim we can now drop this entire conditional part and that this is not conditional anymore. And the reason we can do this is twofold. Number one, we have used up the information that capital G1 equals little x. I already plugged that stuff in on the left side of the conditional line. But that alone is not enough for us to drop this information, because if G2 happens to be a kind of random variable that depends on the value of G1, then I would still need to know this information to compute a probability involving capital G2. However, capital G1 and capital G2 are independent, so once I've plugged in that capital G1 equals little x, not only is there no more capital G1 over here, but the only random quantity on the left side of the conditional line is independent of what's on the right side of the conditional line, so it's no longer relevant. How am I going to deal with this other piece of information in here? This looks a little strange because there's no random variables in here. We've seen things like this before. The probability that a random variable x equals 3 and 1 is less than or equal to 5 is just the probability that a random variable capital X is equal to 3, because 1 is always less than or equal to 5. Whereas the probability that a random variable x is equal to 3 and 1 is greater than or equal to 5 is 0, because 1 is never greater than or equal to 5. So if x is between 1 and n inclusive, then this statement is always true, and it's kind of irrelevant to write it. This joint probability is just the probability that this happens. Whereas if x becomes greater than n, then this statement is false and the whole probability is 0. This is effectively going to just cut down the region that we're summing over, and we end up with the sum as x goes from 1 to n of the probability that capital G2 is greater than n minus x times p times 1 minus p to the x minus 1. So here I have 1 minus the CDF of a geometric 1 random variable with parameter p, and I am evaluating that CDF at n minus x. This is going to look like this. And after we do some cancellations, we've got some 1s here floating around. 1 minus 1, that's going to go away. I have positive 1 minus p to the n minus x. I have another 1 minus p to the x minus 1. When I multiply those, I get 1 minus p to the n minus 1. I also have a little p that can come outside of the whole thing. So we are left with little p times the sum as little x goes from 1 to n of 1 minus p to the n minus 1. So before you start trying to do a finite geometric sum, note that there are no little x's in this expression. So if I sum this as x goes from 1 to up through n, I'm just taking 1 minus p to the n minus 1 plus 1 minus p to the n minus 1 plus, so all I need to do is count the number of terms in the sum. There are n terms here, and this sum is n times 1 minus p to the n minus 1. And lo and behold, this is n choose 1, p to the 1 times 1 minus p to the n minus 1. This is the expression that represents the probability that x equals 1 if x had a binomial distribution with parameters n and p, and that's what we wanted to show. So I'm going to leave this proof here. There are more cases to show, and there are maybe slicker ways to show it and ways to look at this in general rather than just going, okay, let's look at x equals 2 now. But yeah, I think I'm going to leave this here so we can get back to the job of simulation. How about the Poisson distribution? If x has a Poisson distribution with parameter lambda, that means that the probability that x equals some little x is given by e to the negative lambda, lambda to the little x over little x factorial, where little x takes on the value 0, 1, 2 on up. And ways to simulate this, we have the infinite interval chopping method. If you want to use this method, and you may want to use this method, note that the probability that capital X equals little x plus 1 is equal to lambda over little x plus 1 times the probability that capital X equals little x. You might find that this streamlines your code a little bit when you're trying to figure out sort of the next probability and the next probability and the next probability. It's not that big of a savings, but the binomial distribution has relationships like this as well. And if you can find ways to streamline your code, why not? But if you do it at the expense of understanding what you're doing, then don't bother. Another result you might use, we talked about the binomial distribution relationship to the geometric, which is one of the lesser known relationships because the binomial distribution is related to everything. But the Poisson distribution has a cool relationship with the exponential distribution, which is a continuous distribution. To show this relationship, you really should take a course on Markov processes. And yeah, I've got one right there, right there. If you want to check that out, but that's some time investment to get to that point in the course. So I'm going to leave this one here, and I don't think it's really much better than interval chopping. And one more, just for fun, result. If you have capital U1, capital U2, etc., IID, uniform 0, 1, and you let capital X be the smallest non-negative integer, such that the product as I goes from 1 to capital X plus 1 of the u sub I is strictly less than e to the minus lambda, then I claim that X has a Poisson distribution with parameter lambda. So that is not going to save you any work, but it is a just for fun result. So that's about all I wanted to say today in terms of simulation. We've covered a whole lot of distributions. Almost any one-dimensional discrete distribution that you can think of can be simulated from using the interval chopping approach. And as you saw, for specific distributions, there might be better methods, and there might be better methods for your particular distribution that you care about. But for all of these, I wanted to talk about a quick and dirty check for discrete random variable simulation results. So if you go back to the first distribution I looked at with a random variable X that takes on values 1, 2, and 3 with probabilities 0.2, 0.5, and 0.3, suppose that I simulate 100,000 values from this distribution, and I estimate, based on the proportions of 1s and 2s and 3s, the probability that X equals 1 I estimate to be 0.19882. The probability that X equals 2 I estimate to be 0.50132. And finally, the probability that X equals 3 I estimate to be 0.29986. The question is, are these results close enough to 0.2, 0.5, and 0.3 respectively? These are estimates of 0.2, 0.5, and 0.3. Now, P3 hat, just as an example, is the proportion of 3s in the list that I have of my 100,000 simulated values. But it's also a sample mean, like an X bar. If you go through my list of 100,000 values and you say, I want to pick out the 3s, I want to return the proportion of 3s, you could instead go through that list and use an indicator variable and have that indicator turn on to be 1 every time you see a 3 and 0 otherwise. And if you do this, what you have are random variables capital I1 for indicator, capital I2 through capital I 100,000, and your P3 hat, which is the proportion of 3s, is really a sample mean of these i's, these 1s and 0s. If you average those, you add them all up and divide by n. That's the same thing as counting the number of 3s and dividing by n. So the P hat is actually a kind of sample mean. And if your simulation is working correctly, these indicators, capital I1 through capital I 100,000, are IID Bernoulli random variables with P equals 0.3, which was the probability that X equals 3. And so if the simulation is working correctly and we have these Bernoulli random variables, note that the expected value of the ith indicator is just P3 or 0.3, and the variance of the ith indicator is P3 times 1 minus P3, or 0.3 times 0.7 or 0.21. And so the expected value of, like, I'm going to call this I bar, the sample mean or the average of the indicators, which looks like this. I can pull out the 1 over n. I can pull out the sum because expectation is a nice linear operator, but every expectation here is P3. And so I got 1 over n times P3. We get P3. And the variance of I bar is the variance of 1 over n times the sum of the indicators. I can pull out 1 over n, but it'll come out squared. And I can't usually pull a sum out of variances, but I can if they are independent. So I'm going to do that. And the variance of any one of these is P3 times 1 minus P3. So when you cancel all your n's here, you end up with P3 times 1 minus P3 over n. So what is the point here? My point here is that my estimator of P3 that I'm calling P3 hat is actually an I bar, where I bar is representing a sample mean of a bunch of indicators. And by the central limit theorem, this has, for large samples, an approximate normal distribution. The mean of I bar is whatever its mean was, which was P3. The variance is whatever the variance for I bar was, which was P3 times 1 minus P3 over n. So if you take P3 hat minus P3 and you divide by the square root of its variance, you have something that has an approximate standard normal distribution for large sample sizes. Now, this means that if you want to look at, say, like a 95% confidence interval, you want to put this value, this standard normal, approximately standard normal value, between the two critical values of negative 1.96 and positive 1.96. In other words, we're going to have this quantity between negative 1.96 and positive 1.96. Now, usually when making a confidence interval, the goal is to figure out what P3 is. And so you want to solve this system of inequalities to isolate P3 alone in the middle, because you don't know what P3 is and you're trying to come up with two random endpoints for an interval of estimated values for P3. However, in what we're doing here in simulation, we know what P3 is. So we're trying to figure out instead where P3 hat should be if our simulation is working correctly. So unlike a confidence interval for P3, I'm not going to take this system of inequalities and isolate P3 in the middle. I'm going to isolate P3 hat. And what I end up with is that P3 hat should be between P3 plus or minus 1.96 times the square root of P3 times 1 minus P3 over n. Everything's approximate here, so often you'll see people using 2 in place of 1.96, which is fine as well. And we're going to consider our simulation to be acceptable if P3 hat is between these two values. Totally known to us, P3 is 0.03, n is 100,000. These are just numbers, and then P3 hat comes out of our simulation, and we can check whether or not it's between these numbers. We can also check the corresponding results for P1 and P3. Now, I say that this is a quick and dirty check because we really should consider our estimates for P1, P2, and P3 all together and not independently. So technically, I should try to come up with some sort of confidence region in R3 for some region in three-dimensional space where the triples, the P1 hat, P2 hat, and P3 hat falls with probability 0.95 or whatever probability I want. And this is super ugly, even for this simple example, and almost impossible for most things I think you're going to want to simulate from. So we're not doing what are called usually simultaneous confidence intervals for P1 hat, P2 hat, and P3 hat. That's why it's just sort of a quick and dirty check, because they really should not be treated as three separate things. But in my quick and dirty check, we got these values for P1 hat, P2 hat, and P3 hat. And given the sort of reverse confidence intervals I just derived, P1 hat should be between these numbers. It is. P2 hat should be between these two numbers. It is. And P3 hat should be between these two numbers. And it is. Sometimes it won't be. If everything is even without approximations and the central limit theorem, you should not fall in here some percentage of the time. Whether or not it's 5% of the time is also a little tricky because of how we did things independently. It is, again, a quick and dirty check. If one of your estimates does not fall in the corresponding interval, I would run my simulation again just to make sure that maybe your estimate is above the right endpoint of the interval, and the next time you run it, it's also above, and the next time it's also above. And if you see something really systematic like that, I would worry. But for this quick and dirty check, sometimes you will fall in the interval, sometimes you won't. Run it again, see if that changes something, and just look for systematic departures from these estimates falling in these intervals. So next up, we're going to talk about how to simulate values from univariate or one-dimensional continuous distributions. Unlike what we saw today, there's not going to be a one-size-fits-all approach. Today we saw a bunch of options for different distributions, but we did have that interval chopping technique that will work for all of them. We're not going to have that in the continuous case, but I think the continuous case is far more interesting. So I usually say I hope to see you in the next one, but I'm pretty sure you won't be able to stay away. I hope to see you in the next one.